All right, section 6.4. Now we're going to talk about rectangles. And you've learned about rectangles when you were a little kid. I remember my kids had a puzzle, and it was like different shapes, and that kind of thing. And I remember teaching my kids, this is a circle, this is a rectangle, this is a triangle, and all that kind of stuff. Now, I didn't teach them this is an isosceles triangle or a scalene triangle or anything, but, I taught them some basic stuff, and it had nothing to do with me being a math teacher. It just, it was one of these puzzle things, and I remember teaching about a rectangle. And when you're a little kid and you're learning about stuff like that, you learn what a rectangle looks like, and you just look at it and say, oh, that's a rectangle. So, for instance, if I did that, what would you say that was before today? You'd say it's a rectangle. But today, yeah, I say before today, because today you can't say that it's a rectangle right now, because you don't really know anything about it. You don't know the lengths of the sides. You don't know the angles. You don't know anything about it, right? Now, when you're a kid, you look at it and you say, oh, that looks like a rectangle. And sure, it looks like one, but we're a little bit more developed now, right? And our thinking is a little bit higher, and we can't just assume that this is a rectangle. By the way, this whole set of lessons in here are all about parallelograms. This is our first one that is a special type of parallelogram. We're going to deal with about 3 different special types of parallelograms. A rectangle is one of them. So every time you see a rectangle, it's always a parallelogram. So what do we know then? If I told you that this was a rectangle right here, if I said that this was a rectangle, and for the symbol for rectangle, there really is none. They just put the word, or sometimes they'll put just RECT for rectangle. But you use all the letters, A, B, C, D. Just like you would name any kind of parallelogram. You can start at any letter, but you got to go around the horn, right? Got to go around. So around the horn, right? So rectangle, A, B, C, D. So if I told you this is a rectangle, just the fact of knowing that it's a rectangle, we know that it's a parallelogram. Okay, so every rectangle, you might want to jot that down somewhere. Every rectangle is a parallelogram. Does that mean every single parallelogram is a rectangle? Obviously not, because our parallelograms are always kind of slanted and that kind of stuff. So a rectangle is a parallelogram, all right? It is a parallelogram. So what do we know about it then? Well, we know that the opposite sides are what? Both pairs of opposite sides. They've got to be what?
Equal.
Come on, I just drew it up here. Look up here. Parallel to each other, okay? They're parallel. What do you know about the opposite angles of this? They're equal to each other. What else do we know? What about the lengths of the sides, the opposite sides? Since it's a parallelogram, it's what? They're equal to each other, right? There's all kinds of stuff. You know that the consecutive angles are supplementary, right? Because we talked about that on parallelograms. So we talked a lot about parallelograms, and everything that's true about a parallelogram is also true about a rectangle. If I put diagonals in here, the diagonals would bisect each other. Because why? Because it's a parallelogram. Everybody understand that? But what's special about a rectangle that's not true about an ordinary, everyday parallelogram? What do you think, Brooke? All the sides? All the angles. Very good. So the difference between a rectangle and an ordinary parallelogram is that all the angles are 90 degrees. And you probably knew that already, but we officially said it. So if all the angles are 90 degrees, that is a rectangle. And that's really the only thing different about a rectangle compared to an ordinary, everyday parallelogram. All right? It's not the only thing different. There's something else I'm going to show you in a second. But as far as the definition of a rectangle, it's just a parallelogram with 4 right angles. You might want to jot that down. So what's the definition of a rectangle? It's a parallelogram with 4 right angles. Everybody with me on that? Okay. Or you could even say it's a quadrilateral with 4 right angles, because if all the angles... Let me think if I said that right. Yeah, I think that would be true. You could say it's a quadrilateral, but I would say more specifically, it's a parallelogram with 4 right angles. Everybody got that? Okay, that's pretty easy. So does it hold true to the parallelogram stuff? Are the opposite angles equal to each other? Yes, they are. Okay. Are the consecutive angles, are they supplementary? Yeah, they are, right? Because 90 and 90, right? This one's 90, this one's 90. So yeah, sure, they're supplementary. On a rectangle, when you're a kid, what did you learn about the opposite sides of a rectangle? That they're always equal. Is that true about this rectangle? Absolutely, because it's a parallelogram, and that has to be true about parallelograms. What about the being parallel? The opposite sides have to be parallel to each other too, right? All that stuff. One thing we haven't talked about was what? The diagonals. So let's put a diagonal here and a diagonal right here. Now, since it's a parallelogram, what do we automatically know about the diagonals? We know that they do what? I mentioned it just a few minutes ago. They bisect each other, okay? So you do know that they bisect each other. But let's take a closer look at the diagonals to this rectangle. What do you, like off the top of your head, what does it maybe look like is true? Because it is. That's right. The two diagonals are actually equal to each other. Everybody see that? All right. If you wanted to, you could do a little quick proof of that. Let's prove that AC is equal to BD. Well, you know it's a rectangle to begin with, right? So look, we've got these two sides equal to each other. Would you agree? We've got these two sides equal to each other. And I've got an angle right here equal to an angle right there. So what's true about this triangle ADC and this triangle ABC? What are they? Everybody see? Look, this triangle right here. Everybody see it? This triangle right here, ACD, and this triangle right here. Which one am I doing? I'm doing... How can you be confused already? Let's shade them in. Well, anyway, it's... Yeah, because that would be overlapping. That's why I don't want to shade it. You're right. Just look at triangle ADC. I'll write it down. That's what I should do. Triangle ADC should be what to triangle BCD? Or yeah, that's right. Yeah, let's do that. Triangle BCD. BCD. Yes, they are congruent. And why are they congruent? Because of what? Side, angle, side. Okay. So if they're congruent to each other, what's true about the corresponding parts? They must be what? They must be equal to each other. So look, AC is corresponding to what? BD, right? So what must be true about AC and BD? They got to be equal to each other. Everybody see that? That's kind of like, it's not kind of, it is. It's a proof. We basically just proved that the diagonals of a rectangle are what to each other? Are equal or congruent, right? Everybody see that? Because CPCTC, exactly right. All right, so we proved the triangle is congruent by side, angle, side, and the corresponding parts of those congruent triangles are equal. So that means that AC equals BD, which means what's true about the diagonals of a rectangle? They are equal. Okay? Everybody with me on that? Now, if they're equal to each other and they bisect each other, we'll call this E. What do you think is true about AE and BE and CE and DE? They have to equal each other too, right? Because if you got two equal things, you bisect both of them, don't you have to be left with four equal things? Yeah? Okay.
Wait, are they all equal, like AE?
So, yeah, AE is equal to that because they're being bisected, correct? But since AC and BD are both equal to each other, if I bisect this one, I must have the same exact sides equal to each other. Follow me? So all four of those are equal. Only on a what, though? Only on a rectangle. Doesn't work with every parallelogram. It only works with a rectangle. So what's true about a rectangle that's not true about regular parallelograms? Well, first of all, it's the obvious, right? The right angles. They have right angles. Alex, what's the second thing that's true about a rectangle that's not necessarily true about other parallelograms? That's right. The diagonals of a rectangle are exactly the same. They're congruent to each other. Everybody with me on that? All right. Look at this. If you wanted to, what's true about this little triangle right here? See this one, ADE? This one right here? And this triangle right here? They're congruent to each other, right? Side, 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 right? Side, side, side. Do you agree? Yeah? All right. And then the top and the bottom, same exact reason, right? Side, 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 side. Or if you wanted to, you could say these are equal, side, angle, side, right? And you could do the same thing here. You could say side angle, side here, whatever. So you've got two sets of congruent triangles inside of there, don't you? All right, so sometimes that's helpful. Well, what's true if they're congruent? Look, if these two sides are equal to each other, that must mean that this angle and this angle equal. Agreed? If these are congruent, then all four of these angles, 1, 2, 3, 4, they're all congruent to each other. Am I right?
Mm-hmm.
Okay. So there's a lot of stuff you know now about a rectangle. And I believe that's it. Yeah. Oh, what if I did this? Let's do the converse of that real quick. Remember the converse? Yeah. So watch this. If I had this right here. Now let's say I did not know this was a rectangle. I did not know that this was a rectangle. W, X, Y, Z. All right? You follow me? I don't know it's a rectangle. I just know I have a picture right here. But I told you that WY equals XZ. Let's say that was given. So if I knew that WY, which is, I think I'm touching the rectangle, aren't I? Is that touching? No, maybe not. Let's see. Yeah, that's good. So what if that yellow one is equal to that yellow one right there? What if I told you they're equal? What do you think that this whole quadrilateral is then? It must be a rectangle. Because look, if the diagonals of a quadrilateral, right, we don't know it's a parallelogram, we don't know it's a rectangle, but if the diagonals of this quadrilateral are equal, then this thing must be a rectangle. So really, if you just know that the diagonals are equal to each other, you know this thing is a rectangle. Let me give you a quick story. I used to watch, I don't watch it anymore, this show called The Yankee Workshop, New Yankee Workshop, you ever see that? This dude, yeah, he makes wood things, you know, and stuff like that. And he's from New England, from Massachusetts or something. He says, okay, I'm terrible at accents, so forgive me. But he's from New England, and so he says, okay, we're going to make this thing a square. He says, we want to see if this thing's square. And for square, what they means is he wants to make sure it's a rectangle, like it's 90 degrees. Instead of measuring this to be 90 degrees, what do you think you can do to show that this is a rectangle? All you got to do is what? Measure the diagonals, and if the diagonals are equal to each other, guess what must have to be true about these angles? They have to be what? Right angles. So what he did, he took just a piece of string. I don't even think he used a ruler. He took a piece of string. He went from here to here, and then he went from there to there. It was exactly the same length. So guess what? He had a perfect rectangle. All right. Let me give you some problems to do, and you can go. Well, we're going to go 10 to 19. We're going to go 26 to 31. And then we're going to go just two more, 39 and 40. That's page 422. And 23. And it's section 6-4. All right, there you go.
Will the following students please
I
come
would.
to the upper school office? Billy McKenzie, Ori Glenn.